to the ZX seminar, the season finale. I'd like to introduce Jordi A. Montañà López to talk about the exact solution of long-range stabilizer Rényi Entropy in the Dual-Unitary XXZ model. So take it away, Jordi.
Hi, thanks everyone for inviting me and to the ZX seminar. And so I'm Jordi. I'm a PhD student at the Max Planck Institute of Quantum Optics, and I will be presenting this work where we show that certain quantities related to quantum magic can be computed using ZX calculus. So this is work that I did during my master's, and it came out from this paper with Dr. Pavel Kos, who was a postdoc at the Max Planck Institute of Quantum Optics. So the main motivation, broad motivation, is that there are people in quantum computation, on the one hand, interested in obtaining some computational speedups for useful problems. And this requires understanding what are the quantum properties, what are the quantum resources that such a quantum computer should have that would make it hard for a classical computer to perform the same computation. On the other hand, there are people working in quantum many-body physics who care about many-body phenomena that are hard to simulate for a classical computer. So this is, for example, out-of-equilibrium dynamics, quantum chaos, thermalization, ground state properties, and would like to use these quantum computers to simulate these regimes that are not accessible to classical computer. So then there's also the question of why is there this complexity and how to quantify the need for these resources, these quantum resources. So this has brought the two fields a lot closer in the past few years through measures of quantum information by realizing that a lot of these questions are related. So one of these quantum information measures that has been very successful is entanglement. So entanglement in a state, here I'm showing some spins and I'm indicating that there is entanglement between some of them by some arrows. And when one measures such a state, one will find that there are correlations in the measurements that are stronger than classical correlations. And this is given by the entanglement in the state. One way of measuring this entanglement is via this bipartite entanglement. And one designates a region A and a region B and traces out one of them. So for example, traces out region B. And then we obtain a reduced density matrix for region A, from which we can compute some measures like entanglement entropy or Rényi entropies. And these Rényi entropies in particular have been very successful, very helpful for studying properties of ground states in one dimension, because it turns out that when they're bounded, at least growing logarithmically with the size of this region A, then there are classical methods to simulate this, to approximate the states, and one can compute many properties of the state from these classical descriptions. So these are matrix product states. So a matrix product state on n spins of local Hilbert space dimension B allows us to write a state more compactly without having to specify all the wave function coefficients, like d to the power n coefficients, exponentially many, which would be inefficient. So instead, one has this picture where at each side there are matrices with A1 through AN, and the coefficients of the wave function are obtained by taking products of these matrices. And this means that one only needs to specify matrices of bounded size. So if we say that this D is the largest of the sizes of the matrices, then we say that we have a matrix product state of bond dimension D, which is some constant. And this can be specified efficiently. But one of them, tracing out region B, one obtains this reduced density matrix for region A. And then one can define different measures of entanglement, like entanglement entropy over here, or Rényi entropies. And this turns out to be very important for the study of properties of ground states in one dimension. It turns out that when these Rényi entropies are bounded as this, then there are classical methods to simulate a lot of these properties, and these methods are called matrix product states. So these matrix product states on n spins of local dimension D, instead of specifying every single coefficient of the wave function, which would require D to the power n coefficients in its exponential, it would be very costly. Instead, what people do is present this kind of ansatz where the coefficients are recovered as products of matrices. So that's why it's called matrix product state. So graphically, one can draw this as each physical site has a set of matrices, and then this bond over here means we're taking the product over them. These matrices have bounded size, and let's call the maximum over the sizes of the matrices D. Then when we say this is a matrix product state of bond dimension D, and it has allowed studying many properties of one-dimensional ground states very efficiently. In particular, the intuition that you should have is that when one makes this kind of bipartition, as we discussed earlier, there will be some entanglement shared across the bipartition. And this is what is captured by this bond dimension D. So if we would like to represent states with more entanglement, this would correspond to a matrix product state with a larger bond dimension. However, we've been talking mostly about ground states, but entanglement entropy has also been used as a measure in many-body dynamics. So it turns out that how this entanglement entropy grows can tell you, can distinguish between different kinds of evolution. So whether it's Anderson localization, many-body localization, integrable or ergodic, there will be different kinds of entanglement growth. And in order to distinguish these two, more general forms of entanglement have been developed. And so this has been the study of entanglement in different dynamics. But there are other properties that are intrinsically quantum that would also be interesting to understand how they grow as time evolves. So one of these properties is nonstabilizerness or quantum magic. So first, let's try to understand what are stabilizer states. So I'm going to focus on qubits, and then we say that stabilizer states are states that one can obtain if we start from a product of zeros by applying only Clifford gates. So Clifford gates form a group, and they can be generated by C0, Hadamard, and S gates. Remember, C0 allows adding entanglement to the state. So this kind of states, stabilizer states, can show a lot of entanglement. Equivalently, Clifford gates can be described as those unitaries that normalize the Pauli group. So here, the Pauli group on n sides means we take tensor products of Pauli matrices and the identity at each side. And then there's also a global phase. However, even though these stabilizer states can have a lot of entanglement, it turns out that there's this Gottesman-Neal theorem that tells us that the time evolution of the states under Clifford gates and measurements in the computational basis can be simulated efficiently. And this is because we are only considering Clifford gates, but these don't generate universal quantum computation. In general, we need other non-Clifford gates. So in particular, this could be the T-gate or Toffoli. And these are gates that will be adding this non-stabilizerness, also called quantum magic. So this is what we would like to understand as a general goal. How does this non-stabilizerness grow under different time evolutions? So first, why has this question not been answered before if people were already looking at entanglement? The thing is that quantifying non-stabilizerness up until a couple of years ago was computationally very hard. So it required doing some optimization over the state of, over the stabilizer states, which is a very large space. And luckily, a couple of years ago, there was this new measure of magic introduced called stabilizer Rényi entropy. And here, how it's computed is one is given a pure state on n qubits. And then we take the expectation value with respect to each Pauli string. Here we don't include the global phase, only tensor products of Pauli matrices. And then there's an extra power of n here given by a Rényi parameter. So this gives each of these Rényi parameters gives a different Rényi entropy. And this can be understood as participation entropy in the Pauli basis. Also, feel free to interrupt if you would like me to clarify anything further or if you have any questions. So this measure has some nice properties. First of all, it's zero only for stabilizer states. It's invariant under applying Clifford gates. So we saw that Clifford gates are those related to the stabilizer gates and states. And in order to add non-stabilizerness, we need a non-Clifford gate. So we don't expect a measure of magic to increase with Clifford gates. And then it's also additive under tensor products. Okay, we said that this measure is more efficient than previous measures, but remember here, we're doing a sum over all the Pauli strings of length n. So in general, this is 4 to the power n terms, which is very costly still. But okay, it's still, there have been many algorithms developed to approximate it more efficiently. And actually, it turns out that for very relevant classes of states, it can be computed much more efficiently. So in this paper, they showed that stabilizer Rényi entropy can be computed as an expectation value of replicas of the state. So this means that instead of going through every Pauli string and computing this quantity and taking the sum, one can take this expectation value with respect to our state, tensor product with complex conjugate of the state, and tensor product like n times. So this means there are 2n replicas of the state. And we take the expectation value with respect to these lambda operators at each side that couple the different replicas. So these lambda operators are just a sum of identity across all the replicas plus x across all the replicas plus z plus here y with the y tensor y complex conjugate. And written in the matrix product state language, if our initial state is given by this matrix product state, then this expectation value can be computed as this contraction, which for matrix product states of one dimension D has this computational cost, which is only linear in the system size instead of exponential. However, remember that we're interested in studying the magic as it evolves with time. And in general, we saw that we'll be interested in integrable and as a further goal to study quantum chaos. But in our case, we'll be looking at an integrable model, which we saw the entanglement entropy grows linearly with time. And this means that the bond dimension will grow exponentially with time. So we cannot apply this framework directly to our case. However, what we will do is use this form of recasting the sum as an expectation value, and then try to simplify the expectation value using ZX calculus. So the first thing that we need to do is express each of these terms in this expectation value as in the ZX calculus. And one thing that we will need is restricting the measure that we looked at. So instead of looking at the full stabilizer Rényi entropy, we will look at the long-range stabilizer Rényi entropy. So this is first, the stabilizer Rényi entropy is extended to mixed states in this way. So here we fix the Rényi parameter to 2. And then it's extended to mixed states in this form. So we write these functions just to have a more compact form of describing it. And then the intuition is one computes the stabilizer Rényi entropy for a region AB, and then removes the contribution from regions A and regions B. So this is reminiscent of mutual information with Rényi entropies, where also the entropy of the region AB is, we subtract that of region A and region B. And this quantity has already been used to detect criticality of ground states in cases where the regular stabilizer Rényi entropy did not detect this criticality. And moreover, it has a very interesting interpretation in terms of this Clifford augmented MPS methods. So we talked about there's this matrix product state classical methods of simulating states with low entanglement, but that might have a lot of non-stabilizerness. And on the other hand, there's this stabilizer formalism that can simulate states with low magic, but might have a lot of entanglement. So people have been proposing these hybrid methods where you represent the state with both a stabilizer and a matrix product state part. And the idea is to be able to distribute the entanglement to be dealt in the Clifford part and the non-stabilizerness to be dealt in the matrix product state part, to be able to represent states with both higher entanglement and higher magic. And how efficiently one can distribute these resources is measured by this quantity, long-range stabilizer Rényi entropy. However, it turns out that for mixed states of qubits, it's not a proper magic monotone because it's defined with respect to a restricted class of mixed stabilizer states. But I will comment later on how this can be extended to a case where it would correspond to, where it could correspond to. Okay, so in order to compute this long-range stabilizer Rényi entropy, we will be focusing on computing these expectation values, these sums that we recast as expectation values. So now first I need to tell you what are the states that we'll be using, what is the time evolution. This will be the dual-unitary XXZ model. First, dual unitary gates are gates that are unitary in time and space. So these are 2-qubit gates. It can be generalized to qubits, but we'll be focusing on qubits. And unitarity in time is the one that we're used to. So a gate composed with its dagger will just give you the identity. And there's also a requirement that they're unitary in space. What this means is that these contractions of the legs on the sides also give you the identity. So this turns out, this might seem like a strong requirement, but it turns out that these dual unitary gates can give rise to, for example, both integrable and quantum chaotic families. So they're quite expressive. And nevertheless, these graphical simplifications have allowed the analytical treatment of many quantities, many dynamical quantities that in general are hard to compute. So, for example, correlation functions, decay of autogs, or other quantities related to quantum chaos. And the strength of why they have been able to obtain these analytical results seems to stem from this simple extra condition. So it's worth to look a little bit into why this condition holds from the structure of the dual unitary gates. So this can be understood, for example, in the ZX calculus, which is a natural framework to understand these graphical rules. So here I'm just flashing the building blocks of ZX calculus, and I'm sure you're all familiar with it. I'm just showing the Z spiders, X spiders, and some graphical rules so that you can get used to my handwriting. And this will allow us to represent our tensor contraction in terms of this language, and then apply these graphical rules and some other derived graphical rules that we will see to simplify the contraction that we need to consider. So let's look at the dual unitary gates in the ZX calculus. First of all, dual unitary gates can be written as using interaction term with a certain strength alpha, a swap gate, and then single qubit unitaries at each of the legs. So these single qubit unitaries are arbitrary, and this part over here has a very natural representation in terms of the ZX calculus. So this can be written as C naught, a rotation in the Z basis, and then another C naught, which gives you just a phase gadget. So now if we look at the unitarity in space in terms of the ZX calculus, what we see is that when we contract these two legs, then we have arbitrary, so this is mixed between ZX calculus and just general gates, but we have here a gate in front of its conjugate. It's a unitary, so it will cancel. And similarly over here, we have this u plus in front of its conjugate, so they will cancel. Now this diagram, we can move this part away. So we're only just rearranging the parts of the diagram to put it in this form. And now over here, we can use the bialgebra rule. And because this alpha has the other minus alpha, and we're going to fuse them, then this just splits using the coupler. So if we remove these identities, again, we have gate in front of its, a unitary gate in front of its dagger, and similarly here. So we just obtain the identity in the space direction as we saw. Okay. Okay. So you might be a little worried about this single site arbitrary gates because they don't play very well with ZX calculus. And indeed, we're going to have to restrict to a particular case of dual unitary gates called dual unitary XXZ gates, which are those without this single qubit unitaries. And we're going to start with an initial state of Bell pairs, and then evolve with a layer of dual unitary XXZ gates with a parameter alpha, and then a layer of XXZ gates with a parameter beta in the even layers. So alpha in the odd layers, beta in the even layers, and then alternate in this fashion to obtain a periodic Floquet circuit. And this is how we're going to obtain our time-evolved states. This gives rise to interacting integrable dynamics. And now we have specified the state, and we have to look at how to express these lambda operators in terms of the ZX calculus. So first of all, these lambda operators, we can decompose them into a part lambda x and lambda z that contain the x and z components. So lambda x is just identity plus x, and lambda z is just identity plus z. And let's see for lambda z how to express it in the ZX calculus. So first, the only thing that we do here is write it in terms of projectors. So the only difference is the lambda z, is the sigma z has this minus sign over here. And then we see that we can write this as a product of three-legged Z spiders over here, together with an X spider coupling all of these legs. So here this identity is acting on this register, and this plus and also this minus are acting on the last register over here. So this means that this whole thing can be written as a tensor product of Z spiders, and then this part over here is just an X spider coupling all of this Z spiders. And in general, we will have this 2n Rényi copies, but it would be cumbersome to draw all of them. So as a shorthand, I will introduce this squiggly notation to indicate that we're only drawing the first copy, but there are more Rényi copies if you want into the page. So similarly, we can write the lambda x in this language. And finally, this lambda tensor can be written in this way in the ZX calculus. And we will need certain graphical rules that these lambda operators satisfy. So I'm not going to prove them, but if we have two lambda operators and join their respective legs by Z spiders, then we only obtain one lambda operator. If we connect the lambda operator's legs the top and bottom leg by a z spider, we kill the x components and we only get the z components. If we have two lambda z in front of each other, we only get one of them. And if they are acting on different qubits, this split. This one is also interesting. So if we have an x spider, and remember here there are tensor product of 2nx spiders, and there are two lambda z's on two sides of this x spider, we can slide it through. And this other way of composing two lambda z's also yields only one of them. So now we know how to express this whole contraction in terms of the ZX calculus. So let's just see one example, a simple example, where we only evolve for one time step, one layer of dual-unitary XXZ gates. And then each of these tensors, remember that there are all of these copies and the even ones are complex conjugated. And we can equivalently write this in the ZX calculus. So now let's go on to our main result, which is the long-range stabilizer Rényi entropy. And we will be computing these quantities Zn in terms of the expectation values. So first of all, we have to define what is the partition of the state. So this row AB will be defined for regions AB, given in this way. So A and B over here is where we will place the lambda operators, and everywhere else we have to trace out in order to obtain this row AB. So this is what we see here. I'm just showing time-evolved state. And in the regions A and B, we see that there are the lambda, while in the rest of the regions outside AB, we're tracing out. So that's why there are identities. If you cannot see the alpha and betas very clearly, it's fine. I just want to give you an idea of how these simplifications work. So the first thing that we see is that we have outside of regions AB, we have some gates in front of their conjugate. So this will simplify. And at the same time, these ones will simplify. And in fact, we will obtain a light cone of gates that simplify. Now we can apply this, this rule that we saw earlier, where if we have this lambda operator, for example, and we follow all the way through around this loop, we see that we only encounter Z spiders. So this means that we can kill the X component and obtain only lambda Z, while in this other orange loop, for example, at some point it will encounter another lambda, so it cannot kill the X component. So in this way, we arrive at this contraction where most of the X components are killed, but there are some of them still left over. And now we will slide out this lambda Z's outside of regions A and B. And similarly for region B. So now that we have slid out most of the lambda Z's, we see that now inside regions A and B, we have the same thing as earlier. So we still get another light cone of gates that simplify. It turns out that actually all of these gates will also be simplified. And let's see, for example, how these gates in the first diagonal simplify. So what we do is we take the lambda Z, slide it out, and then this phase gadget with the minus beta, we bring it over here, and the one with beta, we bring it over there. And now since they're in front of each other, as we saw earlier, they will cancel. And we bring back the lambda z to its original position. So effectively what we've done is remove the beta and the minus beta over here. So what we saw is the simplification of this guy and this guy, but the same thing holds for this whole diagonal. And actually the same thing holds for these other diagonals as well. So we can remove all of those gates, and actually around this loop, now there's only sigma z spiders, and it turns out that we can also remove this loop because we bring this spider over here, slide it up to the top. It gets into a loop, which can be contracted. And so we have removed this leg. So we can do this in most of these legs. And then we only obtain certain legs that cannot be removed. So now you're going to have to trust me a little bit to squish this diagram in a way that is easier to understand. So the next step is just a rearrangement of the gates. I'm not using any other rules. So the previous diagram is equivalent to this, which we see that in the center part is dependent on time, but the end parts are not dependent on time. So as long as we can implement the contraction of each of these tensors in the center, we can just keep applying it to itself until we reach the desired time. And this means that, remember that each of these tensors has the 2n Rényi copies. So if we can write it, for example, as a matrix of size 4 to the power 2n times 4 to the power 2n for small Rényi indices, we can perform this contraction efficiently or linearly in time, while the original contraction for long times and large system sizes cannot be, or we don't know methods to compute that numerically. So this is already interesting because we've been able to use the X calculus to simplify contraction that is hard for a computer to do in general into something that it can compute efficiently. But it turns out that we can do more. So actually, I'm not gonna, or I can show you if you're interested, but we end up, we keep simplifying until we end up obtaining actually the exact result for this contraction. So here, the zeta n is the contraction that we were trying to obtain, and it can be shown to be depend exponentially in time. This comes from applying each of these tensors as many times as needed. And then it depends on these two functions, f and g. Here, j odd and j even are just proportional to the alphas and betas. And this means that we can obtain the long-range stabilizer Rényi entropy exactly. So this partition we chose because it's the minimal partition where the long-range stabilizer Rényi entropy is non-zero. And in this case, the stabilizer Rényi entropy of region A is just 0, but this one is non-zero. So this is what we compute. And there are other partitions where we also have numerical results to where this one is non-zero, but this is the simplest case that I wanted to show. And this is interesting because in general, computing the long-range SRE is exponentially costly in the Rényi parameter and also in time, as we saw earlier, because the bond dimension grows exponentially in time. And then the bond dimension depends and the complexity depends as the bond dimension to the power n. So this would have been, we wouldn't have been able to obtain this numerically, but using the X calculus, we've been able to simplify it enough that we can even obtain the exact result. So here we see that, in fact, the long-range stabilizer Rényi entropy equilibrates really quickly to this maximum state, this maximum value of 2 log 2. And here, how you should read this graph is that, remember, we applied the alpha and beta gates. Here we're going to set them to be equal. And then as we tune this parameter alpha or j from 0 to pi over 4, this would correspond to the cases of the XX model and swap gates, which are stable, which don't add any magic because they're Clifford gates. And then over here, this would correspond to a rotation by pi, and pi over 8 corresponds to a rotation of the T gate. So that's why we have here maximum magic. So maximum long-range stabilizer. Remember that for mixed states of qubits, it's not a proper measure, a magic monotone. So this is really interesting because it has writing the stabilizer Rényi entropy in this form has allowed studying new magic in a new way using the ZX calculus, while a lot of the previous research was focused on optimizing parts of a circuit to minimize the number of T gates, for example. And now using these new rules for the stabilizer Rényi entropy, and one can study actually also other measures of magic based on stabilizers. For example, stabilizer linear entropy or non-stabilizing power of a unitary operator. And all of these are based on this lambda tensor, for which we have graphical rules. And finally, restricting to first, we had to take a couple of restrictions. The first one is looking at the long-range stabilizer Rényi entropy. Second one is looking at a particular model, the Dual-Unitary XXZ. And then looking at a particular partition of the state. But this partition, we also show numerically that you can change it a little bit and it's still efficient to compute with a classical computer. But this would be interesting to generalize, perhaps to compute the full stabilizer Rényi entropy or to compute it for other models. In the original goal was to compute it for the full family of dual unitary gates, because as we said, this include both integrable and quantum chaotic models. And there has been a lot of interest in understanding how magic grows in integral versus chaotic models. So what is the role of magic in quantum chaos? So actually, yeah, and actually my co-author Pavel has some work on this. But this has already spun new research. In particular, there is this work by my coworker and my co-author Pavel, where they propose a new measure of magic for operators instead of states, evolving in the Heisenberg picture, and using the simplifications of the ZX calculus for the lambda operators, they are able to obtain exact results in this case as well. Another very interesting extension could be that in odd prime local Hilbert space dimension, so instead of looking at qubits, one could look at qubits, for example. And in this case, it turns out that SRE, the stabilizer Rényi entropy, corresponds to Rényi entropies of mana, which is a magic monotone even for mixed states. So in that case, one could have stronger conclusions because the long-range stabilizer Rényi entropy, one could say that for the mixed states, it still quantifies magic. But even still, the long-range stabilizer Rényi entropy quantifies how efficiently this hybrid and matrix product state and Clifford joint methods, how efficient one can do this decomposition. So that is a very interesting line of research that has started in the past few years. And finally, there is still a lot to be understood about how entanglement and magic is generated in many-body dynamics. This is the overarching goal. And we hope that these new tools help answer some of the questions in this area. Okay, so thank you. And if you have any questions, let me know.
Yeah, let's thank Jordi for the talk. Whether you want to turn on your camera and clap or do a clap emoji. Yeah, thank you very much. And yeah, as Jordi mentioned, the floor is open to any questions.
Hi, I have some questions. So I was really also first of all, thank you for the talk. It was super nice and super interesting. I was also really interested in matrix product state, and in the past I was kind of studying this chaotic and integrable system. And as you have said in the beginning, there is always this kind of, for chaotic system, you have that the local operator entanglement grows linearly and the integrable case grows kind of logarithmically with time. So also, as you have mentioned it, your other collaborator has a paper relating the stabilizer entropy, the stabilizer entropy in the Heisenberg picture. Have you thought of trying to use this kind of same analytical approaches in that particular case?
Yeah, so that's a really interesting question. So they actually do that, and they are able to compute for the dual-unitary XXZ case how the scaling of this entropy grows, and they show that there is, while in there are some results for how the stabilizer Rényi entropy for states now grows typically, and it typically grows really fast, so exponentially in time. It equilibrates very quickly, and they show that in this paper that you mentioned, that in the Heisenberg picture, there's this light cone that means that the magic will grow at most linearly. So they actually can compute this kind of thing exactly.
That's super cool. But for instance, how difficult is to apply this kind of analytica? Like here, you are using the fact that you are working with the dual ZX system, which is really symmetric and diagonal. How difficult will be to map this, for instance, in the Heisenberg picture for the same model?
It can be applied very similarly. So in that case, one starts with local observable, so even just one side, and then maybe I can draw. Yeah, so you have one observable, and then you apply all these gates similarly, and then you see that because there are identities everywhere over here and everywhere over here, this creates an effective light cone. So these gates you can replace by the dual-unitary XXZ, for example.
Nice. And do you think that you could get then also analytical expression as the one that you have obtained in this particular case?
Yeah. I think this is one of the results they have, and I think what would be also interesting is to see the distinction between the integrable case for this dual-unitary XXZ and the more general dual-unitary model.
Yeah. And also related to this, here you are focusing the dual XXZ, but specifically, where are you using the dual property?
Right. Okay. So maybe it's a bit hard to see because it's a bit hard to see because it's like once you rewrite it in this calculus, then the dual unitary property looks or somehow you can move things around, so it's not so static that you see it only from one side. So it's hard to say like exactly where it happens. I think when we are able to, there's this step where
Yeah,
we're able to move these things around. And so here you can also think that you have this, I mean, you don't need to move it around. You can just think, okay, there's this line connecting all the way down. And then there's this other line connecting all the way down. So in some sense, you have this gate connected on the side with this one. I think probably this is where you can see that the dual unitary property is happening. It's taking place.
Thank you very much.
Yeah.
Okay, if there aren't any questions for now, I'll jump in with one. Yeah, so it seems like this technique worked really well for the dual unitary XXZ model. And I was wondering what the next sort of models you might have in mind are that are promising for applying these techniques.
Yeah. So, well, the first thing would be generalizations to more qubits with odd prime local Hilbert space dimension, where I think a similar form of phase gadget with a swap gate could give you maybe similar results. It would remain to be seen whether the generalized lambda operators would satisfy similar simplification rules. But then one can also think about maybe time evolutions given by more like CCZ, but like control Z gates. And in this case, maybe one could use the GH calculus to simplify things. But it is hard to, it's hard to find these exactly solvable models.
Yeah. And in that case, is there any apparent way that you could, for example, find inexact solutions or use approximations to make it easier?
Yeah, this is really interesting. So maybe what could be interesting is that, okay, actually, we arrived in to this form of diagram pretty quickly, but then getting to like these exact expressions took a considerable amount of time. But then you see that, for example, this term over here decreases much quicker than this one because it has the 2 t, and these f's are less than 1. So one could think, okay, maybe I don't care about this. Maybe I can say, as long as this is smaller than some number, let's just get the scaling from the leading factor. And so I'm not sure exactly how one could do that from the diagram, but it would be really interesting if one could say, for example, okay, I don't know, remove some part of the diagram. Like, let's remove these two terms. Maybe they're hard to like they lead to harder diagrams. But if I can remove them and I can ensure that the resulting diagram is close to the original one, then that would be really interesting. But I don't know how one could quantify that in general.
No, it's really cool. Thank you. Are there any more questions for anyone? Okay, it seems like there are no more questions. So,
Sorry, I have
of course.
another one.
Yeah.
Also, I was thinking like this kind of tensor, you said that it's really expensive to construct it with tensor network, for instance, like methods. But I have seen in methods for MPS to try to simulate also dynamical evolution that when you have like really repeated structure and this kind of dual structure, what you can do sometimes is fold it in a new tensor that it's more close to each other. Have you tried numerically to see if this will be possible here or?
Yeah. So actually, this is the technique that we follow. So in this case, we show that once you have this, as you say, once you have this structure of one thing applied to itself like many times, and the crucial thing is that the size of each of these tensors doesn't grow with the system size. So this, as we saw, has a size that grows with the Rényi index. But if we say, okay, let's take only small Rényi indices, then it's a tensor of bounded size. And yeah, you can fold this and then consider this whole tensor, apply it to itself many times, and then apply this end caps over here to obtain the final contraction. And that's how we obtain, for example, this exact numerics. So this crosses over here. And then these ones are obtained by some sampling algorithm.
The sampling with Monte Carlo I will support.
Yeah.
And then another question is, what you are describing is this kind of in walls of tensor networks, I think that it's a transfer matrix, right? You have some transfer matrix. If you have infinite system, you then can also kind of find a fixed point with this method and see the behavior.
So this is really good. This is a really good point, and actually, this is how we started to think about this problem when we were trying to compute the full stabilizer Rényi entropy. So in this case, for example, here we are trying to compute the full stabilizer Rényi entropy, and you look at this tensor, and it's, as you said, the transfer tensor that you just apply many times. And if you can show that there is one leading eigenvalue and the others are smaller than this one, so then when you apply it to itself many times, and then n goes to infinity, let's say big N, then this is approximated by the leading by the left eigenvector and then the right eigenvector corresponding to this. So actually we were able to obtain this, I think I have it in the appendix. We were able to obtain an exact result for this transfer tensor for only one layer. And then here what we show is that these left and right eigenvectors actually turn out to be lambda. So if you just apply lambda over here, you get out lambda with a particular coefficient that is maybe I can show it. I had to split it because with all these drawings, the size of the presentation was too large.
Yeah.
So okay, so in this case, when we only have one layer, can you see still my screen?
Yeah.
Okay, so in this case, okay, remember now that we have this transfer tensor, and then we're going to apply this lambda on the right. And actually, I mean, maybe I don't need to go through the whole contraction, but using ZX calculus, you can show that at the end, you end up with lambda again, and then some coefficient here. See that it doesn't have any free legs, so this is just some number, and this number is this. So that's how we obtain that's how we can obtain the that's how we can obtain the stabilizer Rényi entropy for only one layer. And then we wanted to do the same kind of thing for many layers, but yeah, we weren't able to find what are the correct eigenvectors, and
yeah, because
that's a good point.
This like first, I can like from the diagrams I can see that in fact this is the leading and right. It's the right and some eigenvector of your transfer matrix. But how you're sure that this is the leading, like the maximum eigenvalue?
Yeah, so we showed this for the cases when we could compute the Rényi index. We showed this numerically.
Okay.
Yeah.
Nice. And how you realize that this was because it doesn't seem trivial that this has to be the leading,
No.
the leading.
Well, so first we had to, we find the eigenvector numerically,
Okay.
and then you look and then you see what it looks like, and then it has a very similar, and then you see, okay, this is a structure that I've seen before, and then at first you don't know exactly what it is, but you end up to this tensor.
And do you have any physical intuition why this should be the vector, or this it's like something that you find?
Yeah, no, I think no. Yeah, I think it just happens to be this, but I cannot really tell you why.
Perfect. Thank you very much for your answers. It was super
Thank you.
nice. Thank you.